Okay, so welcome to section 4.6, which is exponential and logarithmic equations. Exponential and logarithmic equations. Logarithmic equations. Okay, so let's recall. One-to-one functions pass the horizontal line test, meaning their graphs are intersected at most once by any horizontal line. So let's consider. Right, we have to plot the graph to use the horizontal line test. So x and y coordinate axes. Let's look at an exponential function. X and y. So say we have, a normal exponential function, something like so. So a to the x. It should be evident that any horizontal line will intersect this graph in at most one point. And if that horizontal line is beneath the x-axis, 0 points. And that's fine, as long as it's at most 1 point. So this implies, so for all a to the x exponential functions, this implies 1-to-1. That is, for all y in the range of the exponential function, there exists a unique x in the domain of the exponential function such that a to the x is equal to y. Okay. So, therefore, if we have, say, a to the m equal to a to the n, this implies necessarily that m must be equal to n. There's only one value in the domain. This is my m equals to n right here, for which the value of the function is a to the m or a to the n. They're both equivalent, right? There's only one value of y for which that is true. Okay, so this is called the one-to-one property of exponents. So let's call this a theorem. So one-to-one property of exponents. Oh, how do you spell exponents? Exponents. Okay, so let's let capital M and capital N be algebraic expressions, meaning they have variables, x, y's, and z's, algebraic expressions. And let's have that little a is greater than 0 and not equal to 1. Then, if we have that a to the m is equal to a to the n, this implies both ways that m is equal to n. Okay? Namely, if m is equal to n, then a to the m is equal to a to the n, and vice versa. So for example, so let's solve the following exponential functions. So solve the following exponential functions, if possible. exponential functions. Okay, so number 1, let's say we have 1 over 125 raised to the 3x times 5 is equal to 25 squared. Squared. Okay, so I'm going to color code this. Let's say I have 1 over 125 raised to the 3x as my first factor. Then we're going to multiply this by 5 to the first power, as my second factor is equal to 25 squared. Okay, so my goal, I notice that these are all powers of 5. So in the purple, this is really 1 over 5 cubed raised to the 3x power times 5 to the first is equal to 25 is actually 5 squared. So I can write this as 5 squared quantity squared. Now in the purple, parenthetical remark, 1 over 5 to the third, if I want to push that 5 across the division symbol into the numerator, I negate his exponent. Remember, when we push him either above or beneath the division symbol, we negate the exponent. So now this is 5 to the minus third raised to the 3x times 5 to the first is equal to, now on the right hand side, when we raise a power to a power, we multiply, so 2 times 2 is 4. And let's do the same thing with the purple. So negative 3 times 3x, this becomes 5 to the minus 9x times 5 to the first power is equal to 5 to the 4. Okay, on the left hand side, now that my base is the same, I can combine these guys into a single exponential expression, namely 5 to the minus 9x plus 1, and set that equal to the right hand side, 5 to the 4th. So now I can use my one-to-one property of exponential expressions, which states that the exponents on both sides must be equal for this to be true. So we have that minus 9x plus 1 must equal to 4. So let's go ahead and subtract 1 from both sides. So we get that minus 9x must be equal to 3. Dividing by both sides by negative 9, we get x is equal to negative 3 over 9, which of course reduces because 3 goes into 9 3 times, so minus 1/3 will be our final answer. So there we are. We've solved for, you know what, let me just put this off to the side here. I don't need to write an extra line. Don't like the formatting of this. Make it neater. Is equal to minus 1/3. Okay, so let's do a second one. Number 2. Let's say we have 64 times 1/2 to the 2x plus 3 is equal to 32. Okay, so 64 in purple. Have the quantity 1 over 2 to the first raised to the 2x plus 3. Oops, what's going on here? What just happened? Oh my goodness. Oh no, what color was that? Oh, it must have been green. Okay. Okay, yes, that's what I was doing. Okay, so this becomes now 32. And I notice that 32 is a power of 2. So what I'm going to do is I'm going to try and write 64 as a power of 2, but I might not know that offhand. But I do know that 64 is 4 cubed, so I'll try that first. I know that 1 over 2 to the first, if I push that 2 into the numerator from the denominator, I negate the exponent. So that's 2 to the minus first raised to the 2x plus 3. And now on the right-hand side, I know that 32 is 2 to the 5th. Okay, going back to the purple factor, 4 is 2 squared, which I'm cubing. Now, the blue factor, when I raise a power to a power, I can multiply. So this will now be 2 to the minus 2x minus 3, and that's equal to 2 to the 5th. Purple factor again, 3 times 2 will be 2 to the 6th times 2 to the minus 2x minus 3 is equal to 2 to the 5th. Oh, come on. 2 to the 5th. So now I can combine these two using the rules of exponents. So this becomes 2 to the 6th minus 2x minus 3 will be equal to 2 to the 5th. Okay, so let's actually move this over on the same page. Let's move this up here. Okay, so combining like terms on the left, we have now 2 to the, well, what is 6 minus 3? It's 3. So this is 3 minus 2x is equal to 2 to the 5th. So I can finally equate the exponents using the one-to-one property. So this is that 3 minus 2x must be equivalent to 5. Let's go ahead and subtract 3 from both sides, so minus 2x is going to be 2. Then let's divide by negative 2, so I get that x is negative 1. And there we are. Okay, so let's do one more for good measure. So number 3. Let's say we have 243 times 9 to the x minus 1 is equal to 3 to the 2x. Okay, so 243 times 9 to the x minus 1 is equal to 3 to the 2x. Okay, so I want to note something, that 2 plus 4 plus 3 is 9. So what that means is that 3 divides 243, which is good. So 3 goes into 24 8 times and into 3 once. So this is 3 times 81 there. And 9 is really 3 squared, which I'm raising to the x minus first. And that's equals to 3 to the 2x. Okay, 81 is 9 squared. And for the blue guy, this is now going to be 3 to the 2x minus 2. When I raise a power to a power, I multiply. So this is 3 to the 2x. Okay, now what is 9? So this is 3 to the first times. 9 is really 3 squared, which I'm raising to the second power, times 3 to the 2x minus 2. Oops. Oh, no. Okay, is equal to 3 to the 2x. Okay, so now we're going to have 3 to the first times 2 times 2 is going to be 4, so 3 to the 4th times 3 to the 2x minus 2 is equal to 3 to the 2x. Okay, I'm going to use properties of exponents to combine all three of these into 3 to the 1 plus 4 plus 2x minus 2 is equal to 3 to the 2x. Okay, so now combining 1 and 4 and negative 2. What do I get? I get 3 to the 5 minus 2 is 3. Okay, so this is going to be 3 plus 2x is equal to 3 to the 2x. So I can finally equate exponents using the one-to-one property of exponents. So I get that 3 plus 2x is equal to 2x. That's interesting, because what happens when I subtract 2x from both sides? I get that 3 is equals to 0. Is that possible? No, that's never possible, right? So this is what we call no solution. So this symbol means empty set. That's why we never write 0 with a line through it, because this is a reserved symbol meaning empty set, i.e., that is, id est. This represents the term in math, no solution, because the set of solutions is empty, hence empty set. So there's no value of x for which this is possible. Okay, so let's do Let's use some properties of logarithms now. So for example, let's solve the following. The following using logarithms. Using logarithms. Okay, so number 1. So let's say we have e to the 2x minus 2e to the x minus 35 is equal to 0. Okay, so I have e to the 2x minus 2e to the x minus 35 is equal to 0. So this might seem a bit confusing right now, so I'm going to do a sneaky substitution. I'm going to let u be equal to e to the x, namely e to the smallest power. Okay, so I claim that this first term here is really e to the x squared. Then I have minus 2 times e to the x minus 35 is equal to 0. So I can replace u as follows. This is now u squared minus 2 times u minus 35 is equal to 0. So now it should be evident this is a quadratic. In u, but that's a placeholder. So all I need to do now is ask myself, okay, what two integers have a product of negative 35 and a sum of negative 2? Well, 35 is 5 times 7, so let's see, positive 5, negative 7, does that work? And it does. So in the first case, using the zero factor property, I have that u is equal to negative 5. And in the second factor, I have that u is equal to positive 7 because we want to set these to 0. But what was u? U was a placeholder for e to the x. This negative 5. And over here we have e to the x is positive 7. Now you'll recall the graph of an exponential function is asymptotic to 0, meaning it's always larger than 0. So this is impossible. This is a no solution over here. Okay, it's not going to let me make this nice. There we go. No solution over there. However, on the right-hand side, having a positive value for an exponential is just fine. So I claim I can rewrite this in terms of a logarithm as x is equal to, well, the base of the logarithm is e, hence this is natural log. E raised to the x is equal to the argument 7. So there we are. We get that x is equal to natural log of 7. And that's the only solution for that logarithmic equation. Sorry, exponential equation. Okay, so number 2, let's say we have 3 times e to the quantity 5x minus 15 minus 7 is equal to 23. Okay, so what do we have here? We have 3 times e to the 5x minus 15 minus 7 is equal to 23. Let's go ahead and add 7 to both sides, so we get 3 times e raised to the 5x minus 15 will be equal to 30. Now let's divide by 3 both sides, so we get e raised to the 5x minus 15 is equal to 10. Okay, so I'm going to need to express this in logarithmic form. Once again, base raised to the answer is equal to the argument. So I claim that this is equivalent to 5x minus 15 is equal to, well, log base e is natural log, and the argument must have been 10. Now verify that to yourself. Base e raised to the answer, 5x minus 15, is equal to the argument 10, so that does work. So now I can add 15 to both sides, so I get that 5x is 15 plus natural log of 10. And then I can go ahead and divide by 5. So x, when all is said and done, is equal to 3 plus 1/5 natural log of 10. Now I could bring the 1/5 into the exponent of 10, but that suffices. That's okay for government work. So number 3. Let's say we have 5 raised to the 3x plus 1 is equal to 7 to the x. Okay, now what do we do here? I need to get the x's out of the exponents, but the bases are different. But we can use the fact that I can evaluate the log of both sides. So it doesn't matter what log we choose, but while I'm at it, let me just do 5 raised to the 3x plus 1 is equal to 7 raised to the x. I'm going to go ahead and use natural log of both sides. So if I evaluate natural log of 5 to the 3x plus 1, what I get then is natural log of 7 to the x. Okay, I'm almost there. So what I need to do now is I need to bring the exponents, because my goal is to solve for x. I need to move the exponents down in front using the power rule. So what this gives me then will be quantity 3x plus 1 times natural log of 5 is equal to x times natural log of 7. Okay, so let's distribute the natural log of 5. So I get 3x times natural log of 5 plus a single natural log of 5. And that's going to be equal to x times natural log of 7. So of course my goal is to solve for x, so I want to move both terms involving x to the left. Namely, I'll have 3x times natural log of 5, from which I'm subtracting an x times natural log of 7. And let's go ahead and put the constant term, natural log of 5, on the other side, so it becomes negative natural log of 5. I can now factor out an x from both terms on the left. When I do, what remains will be 3 times natural log of 5 minus natural log of 7. And that is going to be equal to minus natural log of 5. And the last step is to divide both sides by that parenthetical remark. So we get that x is going to be minus natural log of 5, all divided by 3 times natural log of 5 minus natural log of 7. Now, of course, I could use properties of exponents to clean this up, and that's up to you if you want to do that. You don't have to, but, for fun, shall we? So this will be x is equal to, so the first thing I'm going to do is let's go ahead and multiply both top and bottom by -1. Only because I don't like negatives in the numerator, so this will be positive natural log of 5 over. Now I can swap the order of the two terms in the denominator. So I'm going to write it as positive natural log of 7 and negative 3 times natural log of 5. Now I'm going to use the properties of power rule to put this 3 back into the exponent here. So I get that x is equal to, in the numerator, natural log of 5 divided by natural log of 7, from which I'm subtracting natural log of 5 cubed, or 125. Okay, so I can use the quotient rule now in the denominator. This becomes natural log of 5 divided by natural log of the quotient 7 over 5 cubed. And we can leave it like that if you like. Now, tell me, is this going to be a difference, given that I have a quotient of logs? And no, it's not. So, caveat, or warning. So natural log of m over natural log of n is not equal to natural log of m over n. So I can't use the quotient rule, so be careful there. Okay? So hopefully that made sense, and that was a little review of what we did in the last section. Okay, so now let's do another theorem. Pardon me. Having troubles breathing. It's a theorem. Okay, so this is going to be the one-to-one property of logarithms. The one-to-one property of logarithms, which property of logarithms, we could show that graphically like we did for exponentials. It has the same justification. Logarithms. Oh, come on. Rhythms. Okay. Okay, so let's let... Did I leave a space in between my theorem on that one? No, I didn't. Okay, no space. So we will do let m and n be algebraic expressions. Algebraic expressions. And let's have a greater than 0 and a not equal to 1. Then, if I have log base a of m equal to log base a of n, this implication goes both ways, and it is that the argument m must be equal to the argument n. And let's also recall something about the domain of a logarithm. So recall. The domain of log base a of just x is positive. That is strictly larger than 0. So let me do a quick recall. A logarithmic function is going to look something like x and y coordinate axes. We know it's going to intersect the x-axis at 1 and do something like so. And it is asymptotic to the y-axis. Right. Looks something like that. So we can see that the domain is necessarily larger than 0. So hopefully we recall that. Okay, so moving on. Let me say log base a of x. Okay, so for example, with that in mind, let's solve the following logarithmic equations. So solve the following. Logarithmic equations. Okay, so number 1, let's say we have natural log of 21 is equal to natural log of x plus natural log of the quantity x minus 4. Okay, so we have natural log of 21 is equal to, gotta change this back to solid, is equal to, let's do natural log of x. My goodness, did I make them all dotted? I think I did. So natural log of x plus natural log of, what color should I use? Let's do orange, quantity x minus 4. So on the right hand side, I can use the product property, the sum. So this is going to be natural log. If it's a sum, I know that this becomes a product, namely the first argument x times the second argument x minus 4. So now I have the same logarithm on both sides. So I can use the one-to-one property of logarithms to state that 21 must be equal to necessarily x times a quantity, x minus 4. So let's distribute. So I get that 21 is equal to x squared minus 4x. Let's set this to 0. So I get 0 is equal to x squared minus 4x minus 21. So I need to factor this. Can I find two factors which have a product of negative 21 and a sum of negative 4? And maybe 7 and 3 would work. So let's do x minus 7 and x plus 3. That seems to work. So now I can use the zero factor property to state that x is either 7 or x is negative 3. But what's the domain of a logarithm? It's necessarily positive. So I know that this is impossible here. So the only possibility is x equals to 7. That's the only value that satisfies that equation. Value of x, rather. Okay, so number 2. Now notice I didn't say no solution here because it's already solved for x and it is not a solution. So why did I use the empty set notation here? Because I had yet to solve for x in the exponential equation there. So that's the difference, if you're wondering. Okay, so number 2. Let's say we have log base 5 of the quantity 3x minus 7 minus log base 5 of x is equal to log base 5 of 10. And let me go ahead and move this down one. No, I guess I don't need to move it down one line. It's okay. Okay, so let's do log base 5 of the quantity 3x minus 7. Let's do minus log base 5 of x and set that equal to log base 5 of 10. So on the left, I can use the quotient rule. So what I get then is log base 5 of the quotient. The positive guy, 3x minus 7, will be in the numerator, and the negative guy, or the negative guy's argument, will be in the denominator. Set that equal to log base 5 of 10, at which point I can use the one-to-one property of logarithms to equate the argument 3x minus 7 divided by x and 10. So this is equal to 10. So let's go ahead and multiply both sides of this equation through by x, giving us 3x minus 7 is equal to 10x. It's equal to 10x. And let's subtract 3x from both sides, so I get that minus 7 is equal to 7x. And then I'll divide both sides by 7, so I get that negative 1 is equal to x. Now, what's the problem? The domain of a logarithm is necessarily positive. So guess what? This equation has no solution. There's no values of x that satisfy this equation. So this is genuinely no solution. I don't like the way that's drawn. Let me make this a bit better. I wish it would autocorrect a bit better. Okay. No, it doesn't want to do it. Okay. Okay, no solution. Empty set. Okay, no solution to that equation. Moving on. So number 2, and let me be specific because -1 is not in the domain. Right, and up here this would be, oh my goodness, because -3 is not in the domain. Right, so not in domain. Okay, so number 3, let's see, was that number 3? No, counting, not my strong side. 1, 2, 3. Where am I? Okay, so let's say we have log of 3x minus log of 9 is equal to log of 11. Okay, well, what's going on here? What is the base if it's not explicitly written? Remember, the base is so common that we omit it in the case where the base is 10. Okay. So on the left-hand side, I can use the quotient rule again. So this will be log of the quotient, 3x, because that's a positive term, over 9. We'll set that equal to log of 11. And I can reduce, because 3 goes into 9, of course, 3 times. So this becomes log of the quotient x over 3 is equal to log of 11. And now I can use the one-to-one property of logarithms to equate their arguments. So I have that x divided by 3 is equal to 11. And I can simply multiply through by 3, and I get that x is 33. And that is positive, so we're set. Okay, I would like to do at least, I don't know, one more problem. So let's get it through. So, example. So let's solve the following. By plotting, not pluing, plotting each side of the equation. Okay, so number 1, let's say we have, pardon me, log base 2 of the quantity, x plus 3 plus 2 is equal to 4. Okay, so we have log base 2 of the quantity, x plus 3 plus 2 is equal to 4. So I'm going to plot the blue equation, then I'm going to plot the purple equation. So I know for the blue equation, what do I have? This is going to be left 3. This is going to be up 2. What is left 3 and up 2? Well, of course, a logarithmic function. So x and y coordinate axes. X and y. So 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay, so normally my logarithmic equation would, oh, I didn't want to do that, would be 1 comma 0, 2 comma 1, 4 comma 2. It would look something like so. And it would be asymptotic to the y-axis. But I'm going to shift that logarithmic equation. Left 3, 1, 2, 3, and up 2. So each point that I plotted, 1, 2, 3, will be left 3 and up 2. 1, 2, 3, 2. Now 1, 2, 3, 1, 2. As will the vertical asymptote be moved left 3. So the vertical asymptote is now here. And my logarithmic equation looks something like so. Note not drawn very well. And I want to know where that intersects the equation y equals to 4. 1, 2, 3, 4. And it's right here. So I claim that the solution is x equal to 1. So x equal to 1. Okay. There's my solution, graphically. Okay, so number 2. Let's say we have log base 3 of the quantity x plus 5 minus 4 is equal to negative 2. Okay, so on the left we'll have blue log base 3 of the quantity x plus 5 minus 4 is equal to, on the right we'll have negative 2. So let's look at the equation on the left. This looks like it's left 5 and down 4. What is left 5 and down 4? Well, the logarithmic equation, log base 3 of x, of course. Okay. So x and y, coordinate axes, 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, so normally 3 to the x would, having issues here, would be 1/3, -1, 1, 0, and 3, 1, something like so, very shallow. But I'm going to move this left 5. So 1, 2, 3, 4, 5. And I'm going to also move my vertical asymptote. Oh, oops, I forgot to move it down. So I moved them 5 left, but I forgot to move them down 4. So let me do that. So let's move these. Did I move that up too? Okay, hopefully I did. Did I move it up too? Or didn't I for this one? 2, 3, 1, 2. Uh-oh, did I not do that right? I might not have graphed that right. 1, 2, 3, 1, 2. No, I did. Okay, just making sure. Okay, so let's see. I'm moving down 4, so let's move left 5. 1, 2, 3, 4, 5, and down 1, 2, 3, 4. Okay. So, there we go. I'm not drawn very well. Oh, that's TurboGraph. So what I'm going to do is just kind of something like so, and then the graph of -2. Well, it does look like it's going to intersect somewhere. But where is the question? Well, if this is 1, 2, 3, 4, 5, 6, 7, 8, 9, then I should go up 2. So it actually intersects right here at 1, 2, 3, 4, at x equals to 4. So x equals to 4 is the solution had I drawn it a bit better. Okay, and we could solve that. Okay, so number 3 last but not least, I'll have this be the last one for this section. Let's do log base 1/2 of quantity 3 minus x is equal to log base 1/2 of x minus 2. Okay. So we have log base 1/2 of 3 minus x, and that's going to be equal to log base 1/2 of x minus 2. Okay, so what's happening on the right? If I have a negative x, so let's deal with that first. What color should I use for that? Let's use this one. So the negative x is a y-axis reflection. And if I have that, I claim that this will be minus of x minus 3. Okay, so if I do that, maybe I should plot some points to show what's going to happen. Now, am I going to go to the right 3 or to the left 3? And that's a question. So let's say x were 0. 3 is a very valid point to have. Okay. But does that mean I can go to the right 3? What happens if I go to 4? So if I go to 4, I'm going to have a negative argument, which is impossible, right? So it does look like this goes to the right 3. So there it is. Kind of figured it out in our heads. Oh no, did I just change that again? So this is going to be right 3. Okay, let's do log base 1/2 of x minus 2, and that minus 2, of course, is right 2. Come on. Okay, so let's look at both of these on a larger graph. Okay. So x and y, we have base 1/2. Okay, so let's do 1, 2, 3, 4, 5. These are just left and right. Okay, no ups and downs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So let's first look at the original graph of log base 1/2 of x. Okay, so log base 1/2 of x is going to be, pardon me, 0, 1, 1. Wait, I'm doing this wrong way, sorry. So it's going downhill instead of uphill, right? So it would be, we'd still have here, but now at 1/2, it'll be 1, at 2, -1, etc. So at 4, -2, so it's going to look something like so. So that's the unreflected and shifted. So what I'm going to do now is I'm going to shift these 3 to the right, but then I'm also going to reflect them about the y-axis, right? So what's going to happen then is I'm going to get something that looks like so. 3, 4, 1, 2. This this now becomes, let's see if I can draw this graph here. Okay, that is the graph of the blue guy. Okay, it's been reflected about the y-axis and then shifted to the right 3 units. Okay, let me draw that a bit better. Okay, so now let's focus on the purple graph. Let's do him dotted first. Okay, so purple graph is going to be the same graph, right? It's just going to be this guy here as well, because they're both the same before we shift them. Okay. Maybe I shouldn't have done that. What should I do? How should I do that? Maybe I'll dash it. So I'm just taking that dashed blue graph again, and I'm going to shift it to the right 2 units. So what do I have here? Right 2. So 1, 2. Make sure this is solid now. 1, 2, 2, 2. So my vertical asymptote is also going to shift to the right 2 units. And notice what's going to happen. Did I mess up on those? Yes, I did. Shoot. Hold on. Counting, not my strong suit. Let's see. 1, 2. It should be here. 1, 2 should be here. 1, 2 should be here. And 1, 2 should be here. Now I can do my vertical asymptote 2 to the right. And go ahead and draw my graph. Finally. So it's going to look something like this. So because these vertical asymptotes overlap by 1 unit, we actually have a value for which these are equivalent. That value is x equals to 1, 2.5. So that's 5 halves. X equals to 5 halves. Just eyeballing it, but let's see if that's true. So 3 minus 5 halves, so that's 1/2. Yeah. And log base 1/2 of 1/2 is 1. But now 5 halves minus 4 halves is 1/2. Yeah, that's true. That is the answer. Okay. Hopefully this made sense to you, and I will see you in the next section.